Hello guys, this is the video on limits and we'll be taking a look at some questions on limits. Let's get down to it. So the first question we'll be looking at is this. We have to take a look at each of these functions to determine which one we should use the one-sided limit for. The first function is the limit of square root of x as x tends towards 0. The second is the limit of 1 divided by x minus 1 as x tends towards 1. And the third one is the limit of 1 divided by x minus 1 raised to the power of 4 as x tends towards 1. The fourth question is the limit of the absolute value of sine x as x tends towards 0. And the last function that we have there is the limit of the absolute value of x divided by x as x tends towards 0. So we use the one-sided limit to evaluate the limit of a function if and only if the function doesn't exist on the other sides of the limit. So what do I mean by that? Say we have an arbitrary function and it has a domain from negative infinity to infinity, for example. Then let's say at a particular point, let's say x is equal to 5. From x is equal to 5 to infinity, if it doesn't have defined values or the functions don't have values for those parts, that is x is equal to 5 to infinity, then it means from x is equal to 5 to negative infinity are the sides for which the values of the functions can be evaluated. Then it's logical to use the one-sided limit, that is the limit as x approaches 5 from the left, since from the right the function is not defined at that point in time. So let's take a look at each of these questions. So starting from the fifth one, we see the limit of absolute value of x divided by x. The function absolute value of x divided by x is defined for every value of x, that is every value from negative infinity to infinity. So this doesn't count. Then the second function, limit of absolute value of sine x. Since sine x is defined and the value ranges between -1 and 1, then it means the absolute value of sine x is going to be defined for all values of x. The only difference is all the values of absolute value of sine x will now be positive. So in the cases where we add some values of x falling in the negative axis, we are going to be having everything above the x-axis when you plot the graph. So that's what we are going to be having there. For the third one, we have 1 divided by x minus 1 raised to the power of 4. X minus 1 raised to the power of 4 is a polynomial, and a polynomial is defined for all values of x. But 1 divided by x minus 1 raised to the power of 4 is not defined at x is equal to 1, because on substituting x is equal to 1, you're going to be having 1 divided by 0, which is an undefined form. But this doesn't mean that the limit as x approaches 1 from the left and the right can't be gotten, because it has values coming from the right and it also has values coming from the left. So we don't have to use the one-sided limit to evaluate the limit in this case. For the second question, limit of 1 divided by x minus 1 as x tends towards 1, the same thing happens there, similar to what happens for 1 divided by x minus 1 raised to the power of 4. It only has what we call a hole or a discontinuity there, a removable discontinuity. We're still going to see that in subsequent videos. So for the first function, limit of root x as x tends towards 0. So if we are using the Cartesian coordinates, which is what we have been using to find or what we have been operating with, values of x that are negative can't be obtained because now you can't evaluate the square root. In a complex number system, this can be evaluated. For instance, square root of minus 4 can be written as 2i, where I is the square root of minus 1. But in this case, we are working with the Cartesian coordinates. So values less than 0, values of x less than 0 can't be evaluated. And for this reason, since the function is not defined for that value, we can consider that value as part of the domain. And to evaluate the limit as x tends towards 0, we have to consider the limit as x tends towards 0 from the right instead. So that is the function we are looking for. So we can write that the limit of square root of x as x tends towards 0 is equal to the limit of square root of x as x tends towards 0 from the right. Now to evaluate this, let us set up a table of approximation. So in setting up the table of approximation, we're just going to set up a table that looks like this: x, then square root of x. So we are taking values of x that are getting close to 0 progressively from the right. So let's start with 0.1. Let's go 0.01 and see that it's reducing. 0.001, then 0.0001. Let's consider these four values, or we could make it 5, 0.00001. So we evaluate the square root of 0.1, we have 0.3162. On evaluating square root of 0.01, you have 0.1000. On evaluating the square root of this, you have 0.03162. On evaluating this, you have 0.0100. And last but not least, 0.003162. If you look at the trend of these values, it's evident that as x tends towards 0 from the right, that is, as it goes progressively, it reduces progressively from 0.1, 0.01, and so on, we can see that the values of square root of x also reduces. Starts from 0.3, and here it's around 0.003162. This is an indication that the more values we consider, the smaller the value gets. It won't get to 0, but it's going to tend towards 0. So it's evident, and we can say that as x approaches 0 from the right, then the limit of root x as x tends towards 0 from the right is the same thing as the limit of root x as x tends towards 0, and this is going to give us 0. And with that, we've solved this particular question. So let's take a look at the second question. In the second question, we are required to evaluate the limit of 3 e raised to the power of 2x minus 1 divided by x as x tends towards 0. When you are to evaluate limits, the first thing we should try to do is substitute the value of x. So on substituting the value of x here, we have 3 e raised to the power of 0 minus 1 divided by 0. And this is going to give us 3 minus 1 divided by 0, which is 2 over 0. And this is an undefined value. So since it's an undefined value, we can set up a table of approximation to examine the limits as x tends towards 0 from the right and it tends towards 0 from the left. This brings back what I said about the functions 1 divided by x minus 1 and the functions 1 divided by x minus 1 raised to the power of 4. So we realize that we can actually find the limits, but the value is also not defined at x is equal to 0. So let's take a look at x as it tends towards 0 from the right. We'll take a look at x as it tends towards 0 from the left, trying to generate the table for everything all at once. We'll also take a look at the value of the function as x tends towards 0 from the right, and we'll look at the value of the function as x tends towards 0 from the left. So for as x tends towards 0 from the right, we have 0.1, 0.01, 0.001, and 0.0001. So here we have minus 0.1, minus 0.01, minus 0.001, minus 0.0001. Then we take a look at the values of the x. We have 26.64 here. We have 206.06 here. We have 2006.006 here. Then we have 20,006.0006. In the case of x tending towards 0 from the left, we also have minus 14.56, minus 194.06. We have minus 1994.006 and minus 19,994.0006. So now let's examine what we have. You can see that the limit of f of x as x tends towards 0 from the right is equal to infinity, because this value increases progressively, and the limit of f of x as x tends towards 0 from the left is equal to negative infinity. As we can see, the value reduces progressively and gets larger. So since the limit of f of x as x tends towards 0 from the right is not equal to the limit of f of x as x tends towards 0 from the left, then the limit of the function as x tends towards 0 does not exist. For the limit of a function to exist, its right-handed limit and the left-handed limit must be equal to the same value, thus making the function have a limit at that point. Let's take a look at the third question. In this question, we have to find the limit of x squared plus 2x plus 3 divided by 3x squared minus 2x plus 4 as x tends towards infinity. So if we substitute infinity into this, it's, for instance, if you substitute to the numerator, you say infinity squared. Infinity is just a concept, it's not a number. You can't perform arithmetic the way you perform arithmetics with numbers. For instance, you can say 1 plus 1 is equal to 2, but you can't say infinity minus infinity is something. You can't really tell. Infinity is just a concept that is used to describe a very large quantity, numbers in this case. So a very large number is what we call infinity. Say for example, you go 1 million, 1 billion, 1 trillion. If you keep going like that, you just keep increasing the numbers progressively without having a defined value, then we can use infinity to represent that. You can perform addition with infinity, infinity plus infinity. That's just saying a large number plus another large number. You are still going to get a large number, so it's safe to say that is infinity. But if we say infinity minus infinity, you're saying a large number minus another large number. You don't know which is larger, so it's difficult to really say this is what this value is going to be. So you can't determine that value, and hence you can't perform subtraction with infinity just as you perform addition. So we're going to be using the same idea here. For the numerator, we could have substituted infinity there. Infinity squared is still going to give us infinity, plus 2 multiplied by infinity, that's still infinity. And in comparison, infinity and 3, infinity is way bigger, so 3 doesn't necessarily have any effect there. So we can say the numerator is going to equate to infinity. But in the denominator, there's a problem because we have a negative sign there. And if we have a negative sign, this is not going to be easy to evaluate since we are working with infinity here. So it's safe to say for this function, we can't substitute infinity to obtain the values of the limit. In that case, what do? We can now try to factorize x squared out since it's common to the both of them. So limit as x tends towards infinity of, when you factorize x squared in the numerator, you have 1 plus 2 divided by x plus 3 divided by x squared divided by x squared multiplied by 3 minus 2 divided by x plus 4 divided by x squared. It means our original question now simplifies to the limit as x tends towards infinity of the function 1 plus 2 divided by x plus 3 divided by x squared divided by 3 minus 2 divided by x plus 4 divided by x squared. Now, what if we substitute infinity in this case? The values of 1 in the numerator and 3 in the denominator won't be affected because they will remain the same. But if we substitute it into 2 divided by x, that's the equivalent of saying 2 divided by a very large number that can't be quantified. So let's even assume a number like 1 trillion. So 2 divided by 1 trillion is going to give us a very small decimal, an extremely small decimal. 1 trillion is 10 raised to the power of 12. So if you are saying 2 divided by 10 raised to the power of 12, so what you are basically saying is 2 multiplied by 0.000 up to you get to the 11 zeros, then 1. So you're having a very small number, a number that is very close to 0. And infinity is even larger than that. So we can see that any defined number divided by infinity is going to give us 0. So therefore, we can say that if we substitute infinity here, we can have 1 plus 2 divided by infinity plus 3 divided by infinity squared is still going to give us infinity. So we don't have to write that. Divided by 3 minus 2 divided by infinity plus 4 divided by infinity. So this is safe to say 1 plus 0 divided by 3 minus 0 plus 0. So it shows that the limit now becomes 1 over 3, and that is going to give us the answer to this particular question. Let's take a look at another question. We are required to find the limit of absolute value of x divided by x as x tends towards 0. So in doing this, we have to establish what absolute value of x is. So the absolute value of x is defined as follows. It's defined as x for x greater than 0 is defined as minus x for x less than 0, and it is defined at 0 for x is equal to 0. So this means that the absolute value of x divided by x is going to be defined as x divided by x for x greater than 0 minus x divided by x for x less than 0 and 0 divided by x for values of x equal to 0. So this becomes 1 minus 1 and 0 for x greater than 0, x less than 0, and for x equal to 0 respectively. We want to find the limit of the absolute value of x divided by x as x tends towards 0. We can try to evaluate the left and right sided limits. So the limit of absolute value of x as x tends towards 0 from the right is going to be equal to 1, and the limit of the absolute value of x divided by x as x tends towards 0 from the left is equal to minus 1, as we can see here. So it means since the limit of absolute value of x over x as x tends towards 0 from the right is not equal to the limit of the absolute value of x divided by x as x tends towards 0 from the left. It means the limit of the absolute value of x divided by x as x tends towards 0 does not exist. So let's take a look at one more question. We're taking a look at one question. We have compute the equation of the horizontal asymptote of this curve y is equal to 2x minus 1 divided by x plus 2. So we're asked to find the horizontal asymptote of a function. I try to evaluate the behavior of the function as x tends towards infinity. What value of y does it tend into? That's what you are trying to ask. So let's try to evaluate the limit of this function as x tends towards infinity. So this becomes 2x, sorry, this becomes the limit of 2x minus 1 divided by x plus 2 as x tends towards infinity. Just like in the one of the questions that we solved, you can't substitute infinity here directly because we're having infinity divided by infinity, which is an indeterminate form. So therefore, we have limit as x tends towards infinity of x into bracket 2 minus 1 over x divided by x into bracket 1 plus 2 over x. So this becomes the limit as x tends towards infinity of 2 minus 1 over x divided by 1 plus 2 over x. We can now have this to be equal to 2 minus 1 over infinity divided by 1 plus 2 divided by infinity. So this becomes 2 minus 0 divided by 1 plus 0, and we have our answer as 2. So it means y is equal to 2 is the horizontal asymptote of the function. That is, as x tends towards infinity, the function tends towards a value of y is equal to 2. Also, in getting the horizontal asymptote of the curve, you also examine the behavior of the function as x tends towards negative infinity. So if we substitute negative infinity into 2 minus 1 over x divided by 1 plus 2 divided by x, you have 2 minus 1 divided by negative infinity divided by 1 plus 2 divided by negative infinity. So this becomes 2 plus 1 over infinity divided by 1 minus 2 over infinity. And this is still going to give us 2 plus 0 divided by 1 minus 0, and this is equal to 0, which means as x tends towards plus or minus infinity, y is equal to 2. Y tends towards 2, y is equal to 2. And therefore, the horizontal asymptotes is y is equal to 2. So here I should have written that y is equal to 2 is an horizontal asymptote of the function. So in a case where you evaluate the values of the function or the limits of the function, sorry, a horizontal asymptote. Oh, not an horizontal asymptote, sorry. So in the case where you evaluate the values of the functions and you realize that you have two different values, it just means you have more than one asymptote for that function. Let's take note of that when we are solving questions. And with this, we've come to the end of this video on limits. I hope you guys enjoy this one, and I would love to see you guys in the next videos where we'll be talking about continuity and differentiability. Thank you.